Welcome to today's paper reading. Today's paper is titled, Can Long Context Language Models Subsume Retrieval, RAG, SQL, and More? This paper, authored by Jinhyuk Lee and colleagues from Google DeepMind, explores the capabilities of long context language models and tasks traditionally handled by retrieval systems, RAG, SQL, and more. The abstract highlights the transformative potential of long context language models, LCLMs. These models can revolutionize how tasks are approached, especially those traditionally dependent on external tools. By natively processing large corpora, LCLMs enhance user-friendliness and reduce errors in complex systems. To evaluate this shift, the authors introduce LOFT, a benchmark for real-world tasks requiring extensive context. The findings show LCLMs can compete with top retrieval systems, despite not being explicitly trained for such tasks. However, challenges remain in areas like compositional reasoning. The study also emphasizes the significant role of prompting strategies and model performance, suggesting ongoing research is crucial as context lengths increase. Long context language models, LCLMs, have the potential to significantly reshape artificial intelligence by enabling entirely new tasks and applications. They eliminate the need for tools and complex pipelines previously necessary due to context length limitations. By consolidating these pipelines into a unified model, LCLMs address issues like cascading errors and cumbersome optimization, offering a streamlined end-to-end approach to model development. However, realizing the full potential of LCLMs requires rigorous evaluation on long-context tasks useful in real-world applications. To address this, the Long Context Frontiers (LOFT) benchmark has been introduced, consisting of 6 tasks across text, visual, and audio modalities to push LCLMs to their limits. Figure 1 provides an overview of the LOFT benchmark, which consists of 6 tasks designed to evaluate the capabilities of long-context language models, LCLMs, in-context retrieval, reasoning, and many-shot learning. These tasks operate on corpora with context lengths extending up to millions of tokens. The figure contrasts the performance of LCLMs against specialized models, such as CLIP for visual retrieval, which typically require complex task-specific fine-tuning or pipelining. In contrast, LCLMs demonstrate the ability to simplify various tasks through the application of corpus in-context prompting, as outlined in Section 3. Table 1 provides an overview of the tasks and datasets included in the LOFT benchmark. The benchmark covers 6 types of tasks across 4 modalities, totaling 35 datasets. For each dataset, the table lists the average length of the candidates and the number of candidates in the 128K version of LOFT. Detailed information about the datasets can be found in Appendices A to C. The LOFT benchmark is designed to encompass a broad spectrum of real-world applications where long-context language models, LCLMs, can be utilized. These applications range from retrieving pertinent documents in response to a query to extracting complex information from databases. A comprehensive list of tasks and their corresponding datasets is provided in Table 1. For each dataset across all tasks, up to 100 test queries, 5 few-shot queries, and 10 development queries are sampled. To assess how LCLMs perform with varying context lengths, LOFT is created with 3 distinct context length limits: 32K, 128K, and 1 million tokens. Currently, LOFT supports 1 million token contexts, but with advancements in state-of-the-art LCLMs, the framework is designed to easily scale to even larger context lengths, such as 1 billion tokens, in the future. To facilitate testing the same set of queries across different context lengths, each dataset is processed to maintain the same evaluation queries across these lengths, with the exception of SQL tasks as detailed below. For retrieval and RAG tasks, a shared corpus is created by including all gold passages from few-shot, development, and test queries, and then uniformly sampling additional passages until the desired context size is reached. This construction ensures that smaller corpora are subsets of larger ones, and gold and random passages are shuffled to prevent positional biases. This approach ensures a fair comparison, as specialized retriever models also use the same corpora for evaluation. Figure 2 illustrates the process of creating a corpus for retrieval and RAG tasks. The corpus is formed by using the gold passages associated with a set of test queries, along with additional random passages. This ensures that the corpus is diverse and representative. The size of the corpus is limited to 90% of the maximum context length, n, which can be 32K, 128K, or 1M tokens, to account for tokenizer differences and reserve space for instructions and formatting. In this section, we introduce Corpus in Context Prompting, CIC, a novel approach that leverages large context language models, LCLMs, to process entire corpora within their context window. The CIC prompting method involves several key design elements. First, task-specific instructions are provided to guide the LCLM's behavior. Second, the entire corpus is inserted into the prompt, with each candidate assigned a unique identifier for reference. Third, few-shot examples are included, which are grounded to the same corpus and accompanied by chain-of-thought reasoning to improve task accuracy. Additionally, the design considers the variation in context lengths and allocates ample space for prompt customization to ensure a fair comparison among LCLMs. Efficiency is also a focus, with CIC prompting compatible with prefix caching and autoregressive models, allowing the corpus to be encoded once without performance degradation. Figure 3 demonstrates the process of Corpus in Context CIC, prompting for retrieval tasks. This method leverages the capabilities of large language models to follow specific instructions, utilize few-shot examples, and benefit from reasoning demonstrations to effectively retrieve and reason over large corpora provided within the context. The figure illustrates how CIC prompting integrates these elements to enhance the model's performance in retrieval tasks. Table 2 presents the main results on the Loft 128K context test set, showcasing the performances of 3 large context language models, LCLMs, alongside specialized models that have undergone task-specific fine-tuning or pipelining. The evaluation metrics vary depending on the task. Text, visual, and audio retrieval tasks utilize recall at 1. The RAG task employs subspan exact match. SQL tasks are evaluated based on accuracy, and many-shot in context learning, ICL, tasks are assessed using classification accuracy. For retrieval tasks involving multiple gold targets, the mRecall at K metric is applied, with K values set at 2, 5, 5, and 3 respectively, as detailed in Appendix A. This table provides a comprehensive view of how LCLMs compare to specialized models across different tasks and modalities within the Loft framework. In the text retrieval task, Gemini 1.5 Pro demonstrates comparable performance to the specialized model Gecko at a context length of 128K tokens. However, performance does degrade when scaling the corpus to millions of tokens. For visual retrieval, Gemini 1.5 Pro outperforms CLIP across all visual benchmarks, maintaining an advantage over CLIP at various context lengths. In audio retrieval, Gemini 1.5 Pro shows comparable performance to Palm 2D across multiple languages, with a notable advantage in Hindi, likely due to differences in pre-training data. Figure 4 illustrates the impact of varying the position of gold documents within a corpus on retrieval performance. The study reveals that as gold documents for test queries are positioned closer to the end of the corpus, performance declines, indicating reduced attention in later sections. Conversely, placing few-shot queries at the end enhances recall, demonstrating their effectiveness in mitigating attention weaknesses. Additionally, co-locating gold documents for both few-shot and test queries consistently improves performance, suggesting the models enhance focus on these specific locations, regardless of their position in the corpus. This finding offers a potential strategy to mitigate performance degradation in large corpora. Figure 5 illustrates the scaling performance of large context language models, LCLMs, in comparison to specialized models across various tasks. The corpus size is scaled from 32,000 to 1 million tokens, and the results are averaged over all datasets within each task. This figure highlights the performance parity between LCLMs and specialized models at different corpus sizes, providing insights into the potential of LCLMs for broader application in retrieval and reasoning tasks. Table 3 presents the closed-book performance of Gemini 1.5 Pro on the RAG dataset. The table highlights the performance differences when compared to the CIC prompting method. Notably, the closed-book performance significantly lags behind that of long context and specialized models, emphasizing the importance of leveraging an external corpus to enhance reasoning capabilities. Figure 6 provides an analysis of SQL reasoning performance by categorizing spider queries based on SQL operators. The figure reveals that averaging operations present the greatest challenge, while counting operations are comparatively straightforward. Additionally, the analysis shows that reasoning over equality conditions is significantly easier than reasoning over inequality conditions. Table 4 presents the ablation results of Gemini 1.5 Pro across various tasks in the Loft benchmark at a 128K context length. The table highlights how the removal of specific components such as the corpus, query, and instruction affects the model's performance. Notably, the average performance is also reported excluding the Argana and Fika datasets due to the absence of passage titles in these datasets. Figure 7 illustrates the impact of increasing the number of examples in the in-context learning (ICL) process, specifically for the Gemini model. In the LB dialog dataset, accuracy improves consistently as more examples are used. However, the results on the BBH dataset are more varied. Tasks that are knowledge-intensive, such as BBH date and BBH salient, show similar monotonic improvements to LIB dialog. In contrast, reasoning-intensive tasks like BBH tracking 7 and BBH web do not benefit from the increased number of examples. These findings suggest that more complex tasks may reach a limit in their ability to learn from scaling the number of in-context examples. In this section, we discuss the ablation studies conducted on the CIC prompt. The first set of ablations includes removing task-specific instructions, which we refer to as generic instruction, and removing chain-of-thought reasoning, labeled as without COT. Additionally, we observe performance decreases when each few-shot example has its own small corpus, termed corpus in each few-shot. Moving on to prompt positioning, placing the query at the beginning of the prompt instead of at the end, known as query at beginning, led to a significant performance decrease. Similarly, replacing monotonic numerical IDs with random alphanumeric IDs, referred to as alphanumeric IDs, and only placing the IDs at the front of the document, without ID echo, also negatively impacted performance. To test the model's reliance on context, we ablated the document content, keeping only the document title and ID, called title only. This significantly degraded performance, indicating the model's dependence on the provided context. Lastly, we studied the effect of the number of few-shot examples on performance, showing an improvement with more examples, and provided qualitative analysis in Appendix G. Figure 8 illustrates the impact of the number of few-shot examples on model performance. As the number of few-shot examples increases, the performance on the retrieval task improves. Specifically, the accuracy rises from 0.76 in the zero-shot scenario to 0.81 when using 5-shot examples. This indicates that providing more few-shot examples enhances the model's ability to perform well on the retrieval task. The evaluation of long context language models, LCLMs, faces challenges due to the limitations of existing benchmarks. Many popular datasets and methods rely on synthetic tasks such as the needle-in-a-haystack retrieval, and its extension to multi-hop QA. While these evaluations are scalable to long contexts, they do not fully capture the nuances of real-world retrieval or reasoning tasks. Some recent benchmarks leverage existing NLP datasets for tasks like extreme summarization and multi-document QA, but these tasks lack the dynamic scaling capabilities of synthetic benchmarks, making them difficult to adapt to very long contexts. Long Alpaca and Long BenchChat evaluate instruction following under long context settings but contain relatively low task diversity and no examples beyond 100K context length. This highlights the need for more comprehensive and adaptable benchmarks. In this study, the authors introduce Loft, a benchmark designed to assess the capabilities of long context language models, LCLMs, in tasks such as retrieval, retrieval-augmented generation, SQL-like reasoning, and in-context learning. Loft allows for dynamic scaling of context lengths up to 1 million tokens, ensuring relevance as LCLMs evolve. Initial results show that LCLMs exhibit retrieval capabilities comparable to state-of-the-art, handcrafted systems, despite not being specifically trained for retrieval. However, the study acknowledges several limitations, including constraints due to computational resources and financial costs, which range from $1,568 to $6,720 for different models. Additionally, the efficiency of these models was not fully evaluated, and the tasks were limited to 1 million tokens, leaving room for expansion into real-world applications involving larger document sets. The authors suggest future work should focus on optimizing the efficiency of LCLMs and scaling the tasks to handle up to 1 billion tokens. Thank you for watching.